All right, we're recording. Woo! So what about that quiz? Let's take a look at it. So now we go back to our new share. Pull that bad boy back up. All right. So what I'd like to do is just kind of go through each question and talk about it, and then we'll talk about your scores and stuff afterwards. So most of the questions were pretty good. Question 5 was rough, and we can kind of talk about why, and it'll make a little more sense why if well, we'll work on that. And we'll see what's going on there. Yeah, so we'll talk through each of these real quick and kind of go from there. All right. This first one is asking to analyze behavior of the graph. The graph of a function is shown above. Which of the following statements about f is false? Well, it's A, it's not continuous. There's a hole. That's a removable discontinuity, so it's got to be it. What's tricky, B is something that's kind of, it's hard to understand why that's not false. It's a relative maximum at x equals A. Well, if you look at x equals A, the actual value there is more than anything to the left or to the right initially. Therefore, it's a maximum. It's kind of a garbage answer. That sucks. But only one of you happened to pick that, so it's fine. And even the one person, it's a trick. And you just happen to get tricked. And that's okay. It happens. So that one's true. X equals A is in the domain of F because when you plug in A, you get whatever that value is. The left and right-hand limit of A are the same thing. They're both going towards this value. And the limit exists. If D is true, E has to be true. So this is the obvious, I don't want to say obvious one. This is the correct answer, hands down. And again, almost all of you got that. And those of you that picked these other things were like, this one, I guess people probably picked it. The person who picked this one was like, well, no, that's clearly not a maximum right there. I'm forgetting about that point. I'm not going to include it and just look right there. And that's, I'm sure what people in part C did as well. I'm not really sure the person who picked that one. I'm trying to think about why someone to justify that. I'm having a hard time. And then this one, it does exist. People probably thought that because it wasn't continuous that the limit didn't exist, but the limit exists. That's all right. Next one. All right. Intermediate value theorem. Again, I didn't explicitly talk about it in class. It was in the reading, and I expect you to do the reading. So a lot of you got it, which is fabulous. So intermediate value theorem, for those of you who might not have read it or are looking for a different way to hear it, says if you have a continuous function, you should get every output on that continuous function on a closed interval that is between the output of the beginning of the interval and the output of the end of the interval. So if you have a value here and a value here and a continuous function that goes between the two of them, you're going to hit every output between them at least once. That's what you're guaranteed. You're not guaranteed how that will happen, but that's what you're guaranteed, is that it'll have at least one solution. We don't know B because we don't know for sure it's a linear function right between the 2 points. And we don't know it attains a maximum. It could, but this is also an open interval. It's not including the endpoints. We don't know for sure it's going to obtain a maximum there. So that's why. Also, we don't know the slope's always positive. You could draw a little sinusoidal thing. Like if I was going to annotate. If I was going to draw something. That little sinusoidal thing I just drew there helps us see why A has to be true. Or if I do a point to a point and draw a line. That's a line, that's not a curve. Between these two pictures, you can see that this has to be the one that's true because this doesn't have a maximum in the open interval. And this shows the other three are wrong or aren't necessarily true. Oh, it's up there. So there's that. Next one. If you have questions about something as we're going, you can just post in the public chat. I'd prefer you post a question in the public chat so we could all benefit from it then. Okay, let's look at this one. Which of the following statements is true? Boom. The limit is 2 because it's all trending towards 2 there. Looking at incorrect answers, this is the value of the function, not the limit. The rest of the function doesn't say that that's what the value should be. That's what the value is. And the limit definitely exists. The left and the right go towards a particular number. So that's why it's that. Boomtown. Ooh, this one. Which of the following does not exist? Limit of x equals 3 does not exist because from the left, it's going to 2. From the right, it's going to negative infinity. So the limit does not exist. Looking at incorrect answers, that limit exists. It's just a sharp point, which later we'll talk about. It's not differentiable there, but we're not at that spot at the moment. 3 from the left. 3 from the left exists. It's 2. And the limit as x approaches 5. It kind of came out weird here, but if you look at 5, the limit exists. From the left, it's approaching that value. From the right, it's approaching that value. So the limit exists. So that's how that one works. All right, the one that pretty much everybody got incorrect. And pretty much everyone just said it was 2. Which is interesting because looking at the graph, I would have picked that one. But we'll talk about why. I think people just picked that because that was the value of the function. So let's talk about why it is that. So I want the limit. So this is a graph of f. I want what happens to f of 1 minus x squared. So let's try drawing. Oh, that's the right pen. So let's say so if I'm going to look at the limit, I should look at a number less than 0 and more than 0. So as x approaches 0 from the left or from the right, it shouldn't really matter. So if I approach 0 from the left of this, let's say I'm using negative 0.5 and positive 0.5. Let's see what happens. Again, this is probably still too large, but it'll help illustrate what's going on. If I plug in this number to here, like if I'm thinking at 0, if I plug that in, I'm going to get 1 minus 0.25. So then I'm looking at f of 0.75. As this number gets closer to 0, this number is going to get closer to 0, which means it's going to be approaching f of 1. So f of 1, this is going to approach 3 here. If I do from the right, again, if I do 0.5, because again, I'm not using the graph, I'm using this. So if I approach it from 0.5, so a number more than 0, I still get 1 minus 0.25, which still has me approach f of man, that was a great parenthesis right there, 0.75, which still approaches 3. So honestly, I think that's a really tricky question. Like clearly, everybody but one person got it incorrect. This is how I would think about it, is the graph is kind of hard and misleading, but it is being careful about how what they put in there. The 1 minus x squared, it's difficult to create a lot of problems like that for you to practice and kind of conceptualize. It's really hard to do that. So what we can do is just practice some different things and try to get your general understanding of things and just be careful of the little pieces. The little pieces are important. Oh, time. I'm going to keep moving. All right. Oh, I'm recording. Sick. Moving on. Which of these is true? From the left, limit exists. From the right, the limit exists. The limit does not exist. Even though there's not a value there, It's still approaching a value, and here it's still approaching a value, but there's two different values, so the limit doesn't exist, and that's why that's the correct answer there. Which of the following does the limit as x approaches 4 of f of x exist? Yep. Nope. So 1 it exists, 2 it exists, 3 it does not. Because 3, the left and the right go to different values. So that's why it's 1 and 2 only. Algebraically, what's that limit? Well, looking at that, if I plug it in, I get 0 over 0. So what I would do from there is factor. And there should be an x plus 3 that you can factor out of the numerator and denominator, and then plug in -3 to get 3/4 as your final answer. You probably have to simplify a little bit, but that's how it'll work out. Again, there's a range of values there. I'm sure the people who picked 0 or like kept thinking in their mind 0 over 0 is 0. And it's not. It's indeterminate because we don't know what it is. We don't know. So, and I'm not sure what the other answers are. I haven't thought about them very much, but that's how I'd approach that one. Hey, look, another one. Again, I would try to factor it. And there's probably x minus 2 that comes out of the top and bottom, the numerator and denominator. And then you can plug in 2 and see what you get. So it should work out. All right. This one. Which of the following statements must be false? There's a vertical line that's an asymptote for the graph. That means this is a vertical asymptote for the function. So since it's a vertical asymptote, the correct definition of that is x must be false. D is, oh, and I'm sorry, C is not false. So let's talk about this. This means that it's going to 0. That's not true. If it's a vertical asymptote, it's going to infinity or negative infinity, something like that. So the part B isn't necessarily must be false. It could be negative infinity. We don't know. But it could be positive infinity, negative infinity. We don't know for sure. Again, we mentioned earlier that a limit can go to infinity or negative infinity, but it also technically doesn't exist when it does that. So just be aware of that, okay? So B and C could be wrong, but they also could not be wrong. But neither one has to be false. A has to be false. D, that's talking about a horizontal asymptote. So we have no idea what's going on with the rest of the function. I could have definitely designed something that has a vertical asymptote there and a horizontal asymptote there. That's not terribly difficult to do. And I can show you how to do that later. And E just says you have an oblique asymptote of some kind, whatever that is. We don't know, but there's some oblique asymptote. So that's the quiz. Coming back. Probably want to know how the grades work out for that. So here's what we're going to do. There were 10 points on the test, on the quiz. If you got 5 or more, you're getting full points. 4, you're getting 90. 3, you're getting 80. If you got 3 or less than 3, you need to have a conference with the teacher. So you need to talk with me, and we'll set up a time. I already have one time scheduled already. But basically after class, it's first come, first serve for when. If you don't reach out, I'm going to reach out and pick a time. So if you got a 3 or less, send me an email, send me a Discord message, and we'll set up a time to chat about each of the little things. And just kind of talk and discuss about what else. So, so I have one tomorrow. Let's see, when did we set that? 12:45. That's the only one I have scheduled so far. No one else has contacted me. I go by timestamps after class, and we'll go with that. Ah, sick. Oh, sweet. Okay. Ah. that's not the one I wanted to get rid of. Oh, where'd you go? There it is. Okay, sweet money. So yeah, again, if you got a 3 or less than 3, you need to talk with me. Just because I want to chat with you. So keep that in mind. Think about that. There's that. So we are going to briefly talk about the next lesson. Bam! How can you determine the slope of a tangent line? The tangent line problem. So we'll be successful when we can determine instantaneous rates of change. That's the big idea here. So you probably recall a bunch of different things about slope. But here are 2 things from pre-calc that we spent a bunch of time on. Average rate of change and instantaneous rate of change. In this class, in calc, I don't want you using the acronyms. I want you to write out the whole thing. And the reason I say that is because while the AP graders might know what AROC and IROC stand for, they might not. And you don't want them to have to make an assumption that you don't know what you're talking about. Because if they don't immediately know, they don't know, and they're going to mark it wrong. And you don't want that, like especially when you clearly know what you're doing. So make sure you say what's going on. Okay, use the full out words. We use the abbreviations because we are just trying to focus on the concepts. Now we need to make sure we're being very clear about what we're saying. But we have average rate of change and instantaneous rate of change. Note the calculation for them is exactly the same. The difference, pun intended, is that for average rate of change, it's a slope between 2 points. For instantaneous rate of change, it's a slope between 2 points, but the horizontal distance between those 2 points is approaching 0. So we're basically just doing the slope at a single point is what that turns out to be. We're not going to do this, but if we want to find out how fast the boulder is when it hits the ground, we can approximate that using average rate of change in some different intervals to figure that out. So the speed when it hits the ground is, velocity, because that is the direction there, is negative 97.984 feet per second. Now I have an equation and I have a time, which was 3.062. The question is, how did I get that? Well, that's you getting the derivative and using getting the derivative, the slope function, aka the derivative, and using it to determine the slope of the tangent line at that spot. And the slope of that tangent line is the instantaneous rate of change, which allows me to determine the instantaneous velocity. Again, the way we developed that is we just had 2 points, x f of x and x plus delta x and f of x plus delta x. And we just wanted the slope between the 2 points. Simplify it a little bit. But then we're like, well, we don't want 2 points, we want 1 point. Now that we have the setup, what's fun we can do is let delta x go to 0 or h go to 0. Bam. This is how we get the slope function. This is how we get the derivative, okay? So this is called the definition of the derivative. Now this dy over dx, what that means is like the change in y over the change in x. Holy crap. I almost said some other words, but I realized I was recording, so I had to stop real quick. But dy over dx, it's essentially just slope. It's just that technically it's the derivative of y with respect to x. You don't need to know that part right now. We'll come back and hit that a little bit later in the chapter about exactly what that represents. But dy over dx, the derivative of y with respect to x is this, okay? This instantaneous rate of change is how we get the definition of the derivative. That is the definition of the derivative. So all these different symbols over here represent a derivative. So we have the dy over dx, we have f prime of x, y prime, dx of y, and d over dx of f of x. Excuse me. So all of these have slightly different meanings, but we generally use them interchangeably. So that's someplace. So that's what I want you to know. I'm just presenting those so you can see them and know they are things. So a brief recap of that. Oh, geez. Secant lines estimate the slope of a tangent line at a point. Then secant lines in general are average rate of change. Find average rate of change. we can approximate instantaneous rate of change using secant lines, using average rate of change. The slope of a tangent line gives us the instantaneous slope at a point. Again, that's average rate of change, instantaneous rate of change. The derivative gives us an equation to determine the slope of a tangent line at a point. That's a slope function. Derivative and slope function. Those are linked, and you may not unlink them. Okay? That's part of the reason when we first learned about slope functions in calculus or in pre-calc, we didn't call it derivative right away because I wanted you to know what a slope function was first, because that's what a derivative is. As soon as you hear the word derivative, people start to forget what a derivative is, like even though you've been doing stuff with it all the time. So I want to really point that out. Okay? Again, the definition of the derivative is this. Now, what that means is that you can algebraically determine what the derivative of a function is by using the definition of the derivative. Now, those of you that were put a lot of thought into lesson 1.3 in particular, will notice that setup. We use that setup in several of those problems, and we algebraically simplified a bunch of things like this in those problems. Okay? So just be aware that we've already done some work with that. So here's your practice. When's it due? When you get it done. If you're not done with your chapter 1 stuff, which most of you, I think most of you are. I know most of you are done with 1.4 the last I checked, like before the quiz. So I'm hoping that most of you are done with through 1.5. If you're not, get work on that. Get work going on those. Again, those are the problems. Make sure you read 2.1. Another thing, this is your first post credits. What post credits are, again, in calc, it worked out really well for us. I try to time out like 25-minute lessons, like interactive or talking or this and that and whatever. I try to do 25 minutes, and then we just have a bunch of time to work. So we're actually going at about the pace we normally would. We're a little slower, but not by much. And that's a non-issue really. But the point is that I also put some extra stuff after this, like after this slide, which are the post credits. So like here, I showed you how I determined, I used the definition of the derivative to find the derivative and then find the slope or velocity at different spots. Okay. So those are up there for you. You can look at them on your own time. There's also several examples in the book. That's why I want you to read the section. As you have questions with those, let me know. We'll work things out. Again, post some questions in the Discord channel for AB, because then we all can benefit from that. And yeah, we can all benefit from that. Last thought. For this, the work is the most important part of this assignment for 2.1. If you submit this with only the answers, I'm not assessing it or grading it. I'm just going to say, nope, try again. You need to show the work for this one. Okay. The work is super, super important for this. And there are other lessons where you will just be able to basically put in answers, but you won't always be able to do that. This is the lesson. You must show this practice. Okay. You must show the work for this. You're not allowed to just give me an answer. All righty. That's all I have for you today. So if you have any more quick questions, you can stick around. Otherwise, we'll see you later, folks.